When we think of motion, we often imagine objects moving in straight lines, a car on a road, a ball rolling across the ground, or a rocket soaring upward. But in engineering, much of the real action happens in rotation. Wheels, gears, turbines, and even satellites depend on rotational motion, and understanding the physics behind it, rotational dynamics, is essential for building systems that move, spin, and stay stable. At the heart of rotational dynamics lies the concept of torque, the rotational equivalent of force. Just as a force causes linear acceleration, torque causes angular acceleration. Engineers use torque in countless ways, from designing wrenches and levers that multiply effort, to calculating how powerful engines must be to turn massive turbines. Torque explains why doors are easier to open when you push far from the hinge and why gear systems can amplify motion to either increase speed or deliver more power. Another key player is the moment of inertia, which measures how mass is distributed relative to the axis of rotation. A figure skater spinning faster when they pull in their arms demonstrates this beautifully. Reducing the distance of mass from the axis lowers the moment of inertia, increasing angular velocity. Engineers apply the same principle in rotating machinery, balancing components so that energy is used efficiently and safely. Flywheels, for example, are designed with carefully distributed mass to store and release rotational energy in engines, stabilizing performance. Rotational dynamics also introduces the powerful concept of angular momentum, which, like linear momentum, is conserved in isolated systems. This principle is not just theoretical, it is used in engineering navigation systems. Gyroscopes, for instance, exploit angular momentum to maintain orientation in ships, aircraft, and spacecraft. Without them, modern navigation and aerospace engineering would be impossible. Civil and mechanical engineers also face rotational challenges in large-scale structures. Wind turbines must resist enormous torques generated by high-speed winds, while rotating cranes and machinery must remain stable under heavy loads. Even in bridge design, the oscillatory rotations caused by wind or moving traffic must be accounted for to ensure safety and longevity. Rotation also brings with it practical issues such as friction and wear in bearings, which engineers must minimize through lubrication and design. Precision in controlling rotational dynamics can mean the difference between a smooth-running machine and catastrophic failure. In essence, rotational dynamics takes us beyond the simplicity of straight-line motion, opening up a world where spin, torque, and angular momentum dominate. By mastering these principles, engineers can design machines that harness rotation for power, stability, and innovation. This video is part of the series, Physics for Engineers, Foundations that Build the Future, an initiative of the Physical Sciences Consultorium. If you enjoyed this exploration, don't forget to subscribe, explore more content from PSC, and join us as we continue uncovering the deep connections between physics and engineering.